In the Chicago area, you'll typically get 12 to 15% non-revenue water that's lost from leaks. That is probably very typical of the Chicago metro area and lake water. As you come away from the lake, yes, some of the stuff much closer to the city gets quite a bit of age to it, and I suspect has higher levels of the NRW than some of the newer systems in the suburbs. So one of the challenges we're facing as an industry, and certainly as much locally in Chicago, is the expectations of both our customers and our regulators. We have an allocation, as all the communities do in the Collier County that take water from the lake, and the expectation of non-revenue water and reducing that non-revenue water has been set and will reduce over time. So as a backdrop to that, you need to have more effective leak detection and ultimately an aggressive infrastructure replacement program. I know as Illinois American Water, we spend quite substantial amounts of money annually in pipe replacement. Not all communities do, and some of those suffer from some pretty high non-revenue water as a result of that. That's a thing that's going to continue to be an emphasis over the next 20, 30, 40 years. The American Society of Civil Engineers has given infrastructure and water a pretty low rating, a D rating, in the last several years as they've assessed it across the country, and it's a reflection of pipes coming to the end of their time. And the need to replace it is kind of exemplified by the fact that you're going to end up with detecting a lot more leaks, you're going to have a lot more violent bursts, a lot more non-revenue water. So there's going to be continued emphasis on that as time goes forward. So.
Utilities are constantly fighting what's called a natural rate of rise, and that's just leaks that naturally form in a pipeline. Associated with that is the economic impact and when you intervene. So in general, you target a leakage rate that you can afford in a utility, and that's different for most utilities. And the thing to know as well is the rate of rise increases with the age of the pipe. You just get more leaks and more wastage as time goes on, and the fight becomes harder. Getting it below what's traditionally an economic level is incredibly difficult. The utility we're dealing with in Illinois, they purchase water. They purchase bulk water that they then resell to their customers. It's up over $5 a thousand gallons. For perspective, if a utility is producing its own water or treating and delivering its own water, we can get down as low as about 35 cents a thousand gallons. So when you're up at the $5, it's quite expensive. And the effect is that any leakage you have gets magnified. When you're actually purchasing the water, you don't have the opportunity to just turn your pumps up a little bit higher to get a little more flow. You actually have to purchase more water. So the economics become a main driver here.
This is an Ecologics installation, so it's a fixed network. It pulls in leak correlation from a series of hydrants, in this case 79, around this Waste Simmons service area, draws in all the signals every night and sends them to this hub, and then sends them off-site through an antenna array on top for post-processing, and analyzes those signals for data noise, for leak signals.
Leaks have a distinct sound signature. Human hearing range, depending on your age and a few other factors, is anywhere from 80 hertz to 16 kilohertz. Leaks occur in specific frequency bands for different materials of pipe. So for cast iron, ductile iron, leaks are typically going to be in around the 300 hertz. It's audible. The human ear can hear it. And it stands out from a normal pipeline operation, which is broad spectrum. You're just going to hear it as static, really. PVC is very low. It's down around 50 hertz or 100 hertz. So it's at the lower end of the threshold of human hearing. In a lot of cases, you can't hear it. Concrete and asbestos cement, they're stiffer and they're higher up in the spectrum. There are two recordings that I have. One, you can hear what the natural background noise of a pipe is, or just what that broad spectrum sound. And then the second one is the leak sound in a cast iron pipe. So you can hear what it sounds like in that 300 hertz range. decided to put our sensor inside existing fire hydrants. Our sensor is able to detect leak noise about 1,000 feet, with sensor spacing at about 1,000 feet going through the hydrants. Overwhelmingly, the lost water is coming from your distribution system, the pipes that are delivering water to end users or customers. With our leak detection node installed in the hydrant, that hydrant now becomes a leak detection device. In the leak detection world, it's divided on the lines of single channel and multi-channel. And in a lot of cases, it's been an either or, and in our case, we do both. Single channel means any single fire hydrant can tell if there's a leak in its vicinity. The fire hydrant listens in the middle of the night for several hours, taking multiple samples over a 2-hour period and determining on its own whether or not it hears a constant noise. If it hears a constant noise over a large window, it's most likely a leak. If we're doing it over 2 hours, we're increasing the probability that what the sensor hears is a leak. That fire hydrant will then give itself a score and say, I most likely hear a leak, and all the sensors in its vicinity will come up with a score as well. Send all those scores up to the server, where it's then processed. And the server will then identify what are considered leak groups, hydrants in an area that all hear something. The ones closest to the leak hear it the loudest, the ones further away hear it the most faint. And once we do that, or once we identify the leak groups, we do the correlation. That's your multi-channel analysis now. That's where you pinpoint the leak. And each step that I'm talking about here, we're increasing the leak detection probability. Whereas in the past, something like a single channel system on its own typically gives you about 50% leak probability. If you call it a leak, it's only about a 50-50 chance that it actually is a leak. In our case, it's dramatically improved by all these steps we're doing. And by all accounts, with the data we have now, we're up in the 90% range, which is what we targeted at the outset of development. Overall, the results in Illinois were very positive. We were able to point to leaks that formed. We were able to show water savings. So it's a dramatic impact on those few leaks, and when you convert that into dollars, you can start to use the metrics I was mentioning before, anywhere from 35 cents a thousand gallons up to $5 a thousand gallons. So being able to work with a progressive utility and a utility that has stronger drivers than most for cost efficiency, and also who has a good sense of their operations and how they work. They were able to point us to a number of things that were non-intuitive. Installing in fire hydrants, for example, even monitoring permanently versus semi-permanent. A lot of people will choose to deploy a number of leak detection loggers in one area, pick them up the next night, and move them around. But really, there's benefits to monitoring it permanently, such as finding leaks as they progress or as they form and watching the progression. We're able to get this feedback from a live progressive utility that really compressed our development time and improved the value proposition for customers, all with an eye to the economics and payback and making it useful for customers right out of the gate.